Hi everyone, my name is Yu Xiang. I'm from the Hong Kong University of Science and Technology. Today I will present our work, Faster and Better Solution to Embed LP Matrix by Tree Matrix. This is a collaborative work with Dr. Lei from HKST and Dr. Yongxin from Beihang University. Here's the outline, and I will start from the background. In general, we have studied the problem of metric embeddings. Metric embedding has played an important role in a vast range of application areas, such as matching and planning. Among all the data structures of metric embeddings, HSD is one of the most popular solutions. At present, existing research has identified many applications of HSDs, including clustering, spatial crowdsourcing, tree planning, privacy protection, facility location. In these applications, the LP metrics are widely used as the distance function. Thus, our paper mainly focuses on the LP metric spaces. A natural question is when or how to use an HSD. It is often used in hard optimization problems in existing work. The general framework is as follows. Suppose we are struggling with designing approximation solutions with good theoretical guarantees for an optimization problem. We can first build an HSD to embed the input metric of this problem. After that, we can reduce the instances on the input metric into instances on this HSD. Then it often becomes easier to solve your problem on the HSD due to its simple and special structure. Here's a real problem in this work. Suppose we are dealing with online metric biparty matching problem, which is widely used in task assignment problem with spatial crowdsourcing. The first step is we construct the HSD of the input metric, a Euclidean space. Then to reduce the instance, we only need to map the locations from Euclidean space to leaf node of this HSD. Moreover, the Euclidean distance is mapped into tree distance, since the metric has been embedded into a tree. Finally, if we compare the theoretical guarantee of simple greedy, which assigns the nearest worker to each online task based on Euclidean distance, and the HSD greedy that assigns the nearest worker to each online task based on the tree distance, we can observe that HSD greedy has a significantly better approximation guarantee, indicating a better effectiveness. Intuitively, constructing the HSD has an impact on the efficiency or effectiveness of HSD-based solutions. For example, the construction of HSD can become the bottleneck of running time, and the distortion, which is the measurement of HSD's performance, affects the approximation ratio. We have also conducted a case study on this online metric biparty matching problem, OMBM as short, and we have three observations. First, by using HSD, the objective of OMBM can be improved. Second, the lower distortion of the HSD often indicates a better objective of OMBM. Last but not least, the construction time of the existing solution can still be improved, especially for LP metrics. For example, as shown in this table, the worst case time complexity of existing algorithms is at least n squared, which means it will become slow when the number of points n is very large. Moreover, our experiments show that the distortion of HSD is only satisfactory for high-dimensional data. Therefore, we are motivated to design faster and better solutions to construct HSD. Next, I will introduce the problem definition. To begin with, we review some basic concepts. The first one is the metric space, which consists of a point set V and the distance function D. The other concept is the tree metric, which is a tree-based metric space. On the tree metric, the distance between 2 points is the sum of the edge weights along the shortest path on the tree. As in the illustration, the distance between the first 2 leaves on this tree is 6, which equals to 1 plus 2 plus 2 plus 1. Given an original metric space S and the tree metric SD, we say ST is an embedding of S when there is a mapping F of point sets V and VT, such that the distance on S is no shorter than the distance on the tree ST. Accordingly, we can compute the stretch of any 2 points, which is the ratio of their distance on ST and their distance on S. Then we enumerate all pairwise stretches and pick the maximum among them to measure the effectiveness of an embedding. Formally speaking, this measurement is known as the distortion. The formal definition of our problem is as follows. We are given an RP metric space, say S. We aim to embed S into a tree metric, say ST, and try to minimize the distortion as much as possible. Now, I will move to the technical part. To begin with, we introduce the definition of hierarchically separated tree, HST for short. HST was first proposed by Battle in 1996. It is a special tree metric with the following properties. The first weight property is that all edges between same levels have the same weights. The second weight property is that the edge weights are geometrically decreased by a user-defined parameter k. For example, k is 2 on the right, which is the most commonly used setting. As for the node property, the HST has exactly a leaves, and each leaf represents a unique point in the input metric space. Second, an internal node represents a point subset. Third, at the same level, the point subsets in the nodes are disjoint. To construct such trees, our solution is designed based on the idea of divide and conquer. Specifically, we divide the space into several subspaces. For example, as shown in the left fig, we can divide the Euclidean space into two parts. Next, we recursively construct the subtree for each subspace. Here, the subtree of any HST also satisfies the properties of HST. Finally, we can simply link these two subtrees in the final HST. Overall, the major technical challenge here is how to decide the space partition. Intuitively, it is closely related to the distortion of HST. To tackle this issue, existing work relies on pure randomization. Unfortunately, due to the exponential size of such space, it is very hard to find a good partition by pure randomization. By contrast, our idea is based on the partial result of distortion. In other words, every time we do space partition, we compute a part of the final distortion and make sure that this partial result is small enough to obtain the global optimal. The major steps are as follows. Suppose the point set V has been divided into several disjoint point sets xi. The distortion can be also computed by this equation. Apparently, the first term can be recursively computed in each subtree. The second term depends on the space partition. So we want to find a partition that minimizes the second term as much as possible. Here's how we do that in the naive implementation of our solution. First, we use bar partitions and enumerate each point in the input space or subspace. For each level I, the searching radius is the same as the edge weight. Then we can partition the point set into yi and xi. Here, yi denotes the points that are closer than ri to v, where v is the center. Xi denotes the remaining points in yi-1. As a result, we can compute the maximum stretch between points in xi and points in yi. Eventually, we can pick the point that achieves the minimum stretch and use it to space partitions. This step is recursively repeated until each subspace has only one point left. Here is an illustration example. Suppose we have iterated P2 as the center. Since the root always represents the whole point set, we start from the second level. Based on the edge weight at the second level, we can derive the certain radius as 8, which is equal to the edge weight. Then y2 represents the points P2 to P6 that are within this circular range. The point side x2 represents the remaining point P1. Accordingly, we can compute the maximum stretch between points in x2 and points in y2 by brute force, which is 11.77, and the current stretch becomes this value. At the next level, the searching radius will be reduced to 4. Now points P2, P3, P5 are still in the circular range. Hence, we use Y3 to represent these 3 points, and X3 to represent the remaining ones, P4 and P6. Similarly, we can compute the maximum stretch between X3 and Y3, which is 8.85, smaller than current strat. Hence, the value of strat is unchanged at this level. This is an illustration example at the 4th level. We can repeat this procedure for other possible centers. After trying all centers, we pick the one which is P2 with the minimum strat. Then we can recursively handle subspaces as follows. At the 2nd level, the subtree for the gray subspace is as follows. This is a subtree for the gray area at the 3rd level. Eventually, we can construct the final HSD. For this framework, we observe that distortion can be better than the state of the art, but the major limitation is that its time complexity is too high. To reduce the time complexity, our main idea is to reduce the time cost for picking the best center. Generally, there are 2 ways. First, we can reduce the computation of the value of strat by leveraging the index for nearest neighbor or approximate nearest neighbor search. Second, we can reduce the number of candidate centers by sampling. Therefore, we first start from the optimization by N or AN. By observing the definition of the maximum stretch between point set X and Y, we can derive that tree distance is always the same, since any leaf in blue subtree and any leaf in red subtree has the same lowest common ancestor, which leads to the same tree distance. As a result, we only need to compute the nearest distance between any point in X2 over the dataset Y2, which can be answered by a series of search. Moreover, we have done the following reductions and proved that this distortion guarantee is still optimal, and the time complexity can be reduced to n cubic log n. Moreover, we also use 2-phase sampling to reduce the number of candidate centers. Eventually, we proved that the sample size of log n is already enough to achieve the optimal distortion guarantee of log n with very high probability. By using both optimization techniques, the time complexity can be reduced to n to the power of 1.5 log n squared, which is lower than state of the art. Next, I will show you some experimental results. We have conducted experiments of construction HSD on 4 real datasets, 4 synthetic datasets under different distributions, and scalability tests with up to 100 median points and up to 100 dimensions. We have compared with 3 algorithms from existing work. Here, FRT is the state of the art. DCSAM is our solution optimized by AN search and sampling. In real dataset, our solution always achieves the lowest distortion. For example, distortions of DCN and DCSAM are 24 times and 12 times lower than that of the SOTA algorithm. Our solution is always the fastest. For example, DCSAM is over 200 times faster than the SOTA algorithm. The sacrifice here is the space cost, which is marginal. In the scalability test with up to 100 million points, our solution still achieves the lowest distortion and the shortest running time. For example, the distortion of DCSAM is up to 10 times to 34 times the existing baselines. DCSAM is 2 to 4 orders of magnitude faster than existing baselines. Finally, here's our conclusion. In this paper, we propose a faster and better solution called DCSAM to embedding LP metrics by tree matrix problem. Moreover, we have made our source code, datasets, and these presentation slides available in GitHub. That's all for the presentation, and thanks for listening.